Yeah, those are bigger. Are those the new lid tables, like the neutrino opacities and stuff?
No. These, like, so when you click on like the microphysics link, it has like whatever the SRO ones are.
Why is this so zoomed in? This is not usually this is zoomed in.
Oh, I guess it's okay. You should use the red marker. That's the only one you can really see on the video.
Well, I brought 2 blue markers.
Or that might work too. But that first black one you're using there, that.
Couldn't see it.
I was streaming. That was fun.
Well, that's why I try to post the notes before lecture, because.
Well, once you switch over to the red marker, I can actually see it.
All right. What am I talking about today? Look at this. I even embedded figures. What? Because that's hard to draw.
Got a slide deck from that teacher. He's got a bunch of them. You can probably see a lot of it.
Is that like the lecture he gave at the summer school here? Yeah.
Oh, you got stuff there.
I've got. I stole them at some point.
But he's got like a few hundred slides in there that have, I don't know how many.
Yeah. He derives the BSSN. I think he went faster than what we're doing here.
Yes.
Low bet. Low bet. We're basically going to take most of a semester to get to what he did in a couple lectures.
Yeah. by the time he gave his, there was people already lost. Who did the it's a gravitational wave one? It looks like that was
Jenny Barnes? No.
No.
I know who you're talking about.
There was something much longer. I probably don't pronounce it.
Yes.
Most people, after the little bit of GR that was in there, they were like, they were done. Gravity waves were that bad. This is a demonstration.
I mean,
this was
we eased into them. This was like a one-time
Yeah.
lecture. This was, you know nothing about GR. We're going to get the gravity waves. Strap in.
This was like what, 4 days, 3 days?
Yeah, summer school, 4 days, something like that. Anything.
And they had, it was supposed to be like a bunch of like 1.5 or 2 hour lectures that each person giving one, they literally trying to cram like a semester's worth of content into that one lecture. And most of them were pretty hard.
Keeps coming back for more. All right, let's see. I meant to tell you all to read the chapter, but that's okay. You can read it ex post facto. But did everyone read chapter 1?
Yeah.
I mean, that's pretty easy.
Read the 1 plus 3.
Did you read that one too? That's what we're going to work on today.
That's for the partly last night, partly this
So we'll see if I can elucidate some of this stuff. There are, in my opinion, when I was reading through this the first time and writing out the notes, a few steps of the algebra that are mysterious. And I'm like, huh? What happened?
Yeah, I think part of that is if you read the preface to the book, they're like, oh, you should have a thorough understanding at the level of this component.
Yeah.
Which is pretty.
To be fair, this is meant as a second course, following a graduate level course in GR. So
we just go and see. Actually,
jump in and swim.
Oh,
I have now, MTW is now on my desk because every once in a while I've got to flip back and go, how's this work again?
This one's got some good stuff in it.
Who's that? Oh, is that? That's all those.
Yeah. It's not quite as terse.
Is that true?
Yeah, it shows a little bit more detail how they get some of the results for some of it. I mean, there's a lot of hydro and numerical stuff in there that's not. Actually, there's 3 really good numerical methods chapters in there, more so than the Shapiro one, but last semester, I was able to use it for quite a few things.
Well, I ain't switching now.
Oh, no. It doesn't cover as much.
Yeah.
As far as just doing numerical GR, but
yeah.
Some of the intro stuff, it's a little.
Yeah, I think this is probably
more expanded.
It's more heavily focused on GR Hydro, right?
Oh, yeah, it jumps. It has a few chapters that are good. It's just kind of introductory stuff though.
I should take a look at that. Yeah, I'll get that book.
Yeah.
So I can go back and augment my
the
notes.
paperback edition.
Is it?
I got ready.
Oh, wow.
Which author was that?
This is Zola and Zanatti. Relativistic.
Solo was David Radich's
Yeah.
PhD advisor.
I think that's where I read this book from.
Thinking of doing. I would think you have to, if you're doing. I can make it, so go as far as you can, and then make sure you have stops to. Oh, this is going to help.
What's going to help?
An idea Ed has for a thesis.
What's the second that's going to help?
Make Mesa 2D.
Huh?
That's what he said.
What is it normally?
1D.
It's implicit Lagrangian.
Oh. You want to do that too? You hate yourself.
Maybe Ed hates you.
That's not soft. Don't listen to his That's like, no, that's not awful.
All right. All right. Let's kick this big. Okay, so today we're going to start with 3+1 decomposition of space-time, which is the foundation for the equations that we'll actually use to solve numerically GR. So I know that Steve's already gotten started on the the midterm project, and he found that I did have a typo in my yeah, that was a typo for sure. It doesn't matter, but I put k equals 3,000. It should have been k equals 30,000 for the polytropic equation state. You know, you get a neutron star that weighs, what was it, 10 to the minus 2 solar masses.
Like its compactness ratio was something like 10 to the minus 6 or something.
It's a wee baby. It's a wee baby neutron star. But with 30,000, you get something more relevant.
Yeah, it's like 12-kilometer radius.
Yeah.
6 solar masses.
Yeah. So that's what I meant to put in there. That's what the original notes had. So Steve's already got the polytropic part working. So proof positive that that first part's pretty easy. And once you do that, the rest is just kind of engineering, right? You don't have to figure out how to solve any new equations. You just got to read in a table, do some interpolation. So we can talk about that some more. My plan was over the weekend to write up a new one in Python. I mean, I've got TOV solvers lying around, but not in Python. So I thought I'd do that myself.
But actually, the question on tail I was thinking about it, because the way it's indexed, because it's also indexed always on the electron fraction. No, we didn't like at equilibrium. Is that the right assumption?
That's right. That's right. That's right.
I wasn't sure.
I mean, let's keep life simple. Yeah. Okay. Any questions before we get going? Before I forget, for next Tuesday, again, I'm not going to have a homework assignment this week, so get ahead of the game, play around a little bit with the TOV solver stuff. It's going to be easy and fun. And next week, I'll assign a homework. Before next Tuesday, please read chapter 2 of Baumgart and Shapiro. We're going to start covering that today. So you'll probably want to catch up with the reading. All right. Let's get down to this. 3+1 decomposition. Now, we've toyed with this already, even in Thorne and Blandford, right? Where we broke things down into a time part and a spatial part, and we did various different kinds of analyses in that framework. What we're going to do now is a particular kind of 3+1 decomposition, just a little more in-depth, a little more detailed, a little more useful for solving the field equations in a 3+1 framework. And there's some nuance to that we have to deal with. So what this will do is make the Einstein equations will essentially become an initial value problem, which that's what we love to solve in physics, right? Give me an initial condition at some instantaneous point in time, and I want to evolve forward in time. Now, that kind of seems obvious to a physicist, right? That's how we want to solve problems. But when you're dealing with a genuinely four-dimensional space-time, where time is just an equal component to the other spatial dimensions, that's not entirely clear, right? That's not an entirely obvious thing to do. And so in order to be able to even do that, we need to develop this 3+1 decomposition, where I've got things that I can instantaneously define at some instantaneous point in time, and from that compute derivatives, specifically derivatives of the metric, because that's what tells me how the metric evolves forward in time. All right? So like we would do in classical mechanics, right, we would start with, if I want to solve for the trajectory of a particle, we'd start with that particle's position and its velocity at some instantaneous moment in time. And with that information, I can integrate forward to get its new position at some other time, right? But here in GR, what we're going to need to do is specify a couple of things. One, the metric, naturally. And then the other thing that we're going to need is the time derivative of the metric. Just like we would do position, velocity of a particle in classical mechanics. In order to integrate the metric forward in time, we need its first derivative in time. And then we integrate. Right? And we can figure this out on some hypersurface of constant time equals t equals, you know, a constant at some instantaneous point, right, for my initial conditions. T equals 0, right? What's this equal to the initial time, right? Then we must compute the second derivative, the acceleration, right? Like I would do anything else in classical mechanics, I need to be able to compute the second time derivative of the metric, which is the acceleration, the analogous, right? Just to take the analogy to almost a breaking point. But solving for this second time derivative is not so simple, it turns out, for some subtle reasons, right? So we would need to do this 10 second derivatives, if you count them. Okay, if you take a look at the Einstein equations and you count how many second derivatives of the metric I need, there are 10 free components. We actually talked about that before, right? There are 10 independent components of the metric when you break it down that aren't destroyed by various symmetries. Okay, and if you take a look at the field equations, GAB is equal to 8 pi TAB, and you count the number of independent components there are 10. So you think, QED, I've got 10 equations, I've got 10 unknowns that I need, I should be able to solve my problem. The issue, however, is that because of the Bianchi identities, which say that the gradient of the metric, or the gradient of the Einstein tensor, I'm sorry, is 0, this actually imposes some constraints on our field equations, right? So this actually leads to the following, which is the partial, I might switch between partial sub t and comma sub t. You all know that that means exactly the same thing. But if I'm switching between those, that means the same thing. Partial I, G A I minus G B C Christoffel symbol ABC minus GAB Christoffel symbol CBC? Does that collapse like that? That must be an ABC. I'll write it the way it's written. Does that collapse to the right? Cancel, 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 cancel. Yeah, that's fine. That's what I meant, right? So this actually eliminates some of the free equations that I have in the Einstein field equations, okay? And that means that some of those terms, if you look at this, do not contain time derivatives, okay? So they're written purely in terms of spatial derivatives and the connection coefficients. And so these four equations of the Einstein tensor, the Einstein field equations, don't have any time derivatives. So I can't use them to solve for the second time derivatives that I need. So from my 10 equations, eliminate 4 of them. They're not useful for solving the evolution equations. Does that make sense? Do I have an index wrong?
The 2 C's on the last one don't make sense.
I don't think so.
One of the C's should be.
So AB, the differentiation index has always got to be the last one.
Yeah.
And so there, that should probably oh wait, is it, hold on.
Yeah, it's the same.
A, B?
Because you don't need to contract on the A though.
You're right. I don't want to contract on the A.
Right for the second term.
Do you think this is wrong too?
You're contracting on both.
Oh yeah. And that's right. And so I want to contract on B and, no, I think it was right the way I wrote it. Because I do want to contract on C and B and end up with A on top. All right, let me make sure that I didn't make a mistake writing this down. That's why I've got this. In-flight correction. We'll edit this out of the YouTube. It'll be fine. Oh, great. This wasn't in the book. I wrote this down. No, I was right. Yeah, because you want to contract on B and C. So it's gamma CBC. Yeah. That's right.
So it looks weird.
It looks weird. It looks weird. But nothing prevents me from doing it. Okay. So I'm down 4 equations that don't provide me any time derivatives. I've lost my notes. Okay. Right. So all of these equations, GA0, no time derivatives. And what that means is, therefore, this set of equations, GA0 is equal to 8 pi TA0, end up being constraints versus evolution equations, right? They're not evolution equations. They don't contain time derivatives. They don't tell me how the metric evolves. But what they do is require that the Einstein tensor components, these 4 parts of the field equations, obey this, right? This must be true, whatever metric I provide, but it doesn't tell me how that metric evolves. So we call that a constraint. All right. Okay. And then we end up with the dynamical equations, or the actual evolution part, which is just Gij is equal to 8 pi Tij. Now where I goes from 1 to 3, right? It's the spatial part, okay? And these are my evolution equations, and there's 6 of them. So I don't have all of the equations I need. And just remember, if you're counting and you think 3 by 3 is 9, why is that 6? Don't forget, that's a G. Symmetry of the Einstein tensor and also of the stress energy tensor. So that symmetry eliminates 3 of the equations, right? Or at least 3 of the degrees of freedom. So symmetry is how we get from 9 to 6 there, for that case. Okay. Now, the appearance of this problem of 10 unknowns versus 6 equations actually is to be expected because of some freedom of choice that we have in these equations. Anyone care to hazard a guess what that freedom is and why it eliminates 4 of the equations? Coordinates. We always have a choice of how to define our coordinates, right? And since it's a 4-dimensional space, it's got to be it's got to be invariant under those coordinate transformations. And so 4 of those equations are tied up solely with that symmetry of the field equation, that freedom of the field equations to arbitrarily define my coordinate system, right? And so that's why 4 of these equations are limited. Another way of saying that more physically is there's gauge freedom. The gauge freedom means that I eliminate 4 of these equations in a 4-dimensional space. Freedom of the gauge, right? Okay. In other words, 4 of these equations aren't physical equations. They're tied up only with how I'm constructing my coordinate system. That's all, right? And so they better not tell me much about physics, i.e. the evolution of the metric. Okay. Now, so if these constraints, GA0 is equal to 8 pi TA0, satisfied initially, then the evolution equations guarantee that it'll be satisfied at all times. Evolution equations keep them satisfied. So that's nice. If I can satisfy the constraints initially, and then I follow these evolution equations forward in time, I'm guaranteed to preserve the constraint. Cool. All right. Another way of saying that is that under these evolution equations, I could say something a little bit more rigorously mathematical, which is the time derivative of GA0 minus 8 pi TA0 is 0. Right. That's satisfied by construction. Okay, so now, let's bust this up. And figure out how we're going to actually use the evolution equations to give me all the derivatives I need. So now our 3 plus 1 decomposition. It's going to have, this is basically a way to turn this into an IVP, or you might see it as a Cauchy problem, right? To take these field equations and make them something that we're used to. We've got the 4 constraints that we have to fold into this system. And they must be satisfied at all times throughout this 3 plus 1 decomposition. And so what do I mean by a 3 plus 1 decomposition? I'm going to draw, and I'm not going to draw 3D because that just gets hard. So I'm projecting all the way down to a 1D space and time. And what I'm going to do is I'm going to create in this space slices of constant coordinate time. So those are still curved, right? They look curved. But in this space, this is all constant time, right? T0, T1, T2, like that. So along those surfaces, those 3 surfaces, 3 volumes, spatial part, the coordinate time is constant, even though it doesn't look like it is. Right? And so I'm going to bust these equations up so that there is a purely spatial part and then a temporal part, so that I can solve these equations. we're going to call these hypersurfaces in some larger four-dimensional manifold. Right? And we'll define some rules. When you bust this up into 3 plus 1, you get some extra equations. So there's actually 12 evolution equations that I can use, okay? And they are a coupled first order system of ODEs. Cool, because I can solve those, yeah. We end up with more free variables that we have to solve for when we do this 3 plus 1 decomposition. That's right. That's right. And then we've got 4 freely specifiable functions that come from our gauge freedom. Okay. So I think the way that everybody, all the way back to Misner, Thorne, and Wheeler, introduced this idea is to use the analogy of the electromagnetism, right? And Maxwell's equations. We'll do that too, to demonstrate a 3 plus 1 decomposition in this sense, okay? So for like the 3rd or 4th time, we're going to do Maxwell's equations. In Minkowski space. So flat space, right? But 4D space-time, but flat. All right. Here we've got a constraint, which I'll call curly C sub E, which is the derivative. We defined this notation last time, right? Of the electric field vector minus 4 pi rho has got to be equal to 0. A constraint on B, which I'll define as the divergence of B has got to be equal to 0, solenoidal constraint. And here, rho is the charge density. And this is the electric field vector. And this is the magnetic field vector. And then recall, have we defined this D yet? This capital D as just being the spatial operator? Yeah. This is the spatial, meaning it's 3-dimensional, covariant derivative. All right? So these are the constraint equations. They contain no time derivatives, right? So E and B must satisfy these 2 equations at all times. But they don't tell us how E and B evolve. So an analogy to our A0 components of the field equations, they are constraints. All right. So then for Maxwell's equations, we have the evolution equations. Which are partial T EI is equal to the curl DI, sorry, that should be a J, D upstairs J, B upstairs K, minus 4 pi, supremely confusing J sub I, that's the current density, little j, but bigger than a subscript J. Partial in respect to time of the magnetic field. This is the induction equation, minus the curl ijk, Levi-Civita tensor of dj ek. Okay? And like I said, I'm going to write this over here so I don't take up any more space on that side. And these are our definitions. J upstairs I is the current density. or the charge 3 current, whatever you want to think of it as. Okay. So now let's do some deriving. So di, I'm going to take the derivative of that first equation. And over here I get di ijk of djbk. I also made everything covariant, which I can do. I can use the metric to make everything covariant, bring everything downstairs, minus di 4 pi current, charge current I. Should that be upstairs? That should be upstairs. Good. Okay. What is divergence of a curl? Of anything? 0, right? So I can get rid of this term right off. Boom, gone. So now I can bring this derivative in, and I've got the time derivative of the divergence of the electric field is equal to time derivative of 4 pi charge current from my constraint, right? So I just use this, which it must be true, is equal to minus 4 pi di j I, like that. So I can get rid of the 4 pi's, easy peasy. All this leads to the time derivative of the charge density plus the divergence of the current is equal to 0. We know that. That's just a continuity equation in the unit, right, for charge. It's just charge conservation. Okay. I don't want to erase my constraints yet. I'll erase my foliation, and we'll draw it again later. Okay. Okay. In order to make this look like a 3+1 set of equations, I'm going to introduce the vector potential, my favorite way of solving the magnetic field. All right, and that's always A, right? And it's a vector, and it's equal to some function. And okay, so here's where the 3+1 split comes in. Okay, so my vector potential is going to be a 4D vector, right? It's a space-time vector. It's 4-dimensional. And I'm going to treat it like it's made up of 2 separate components. One, a time component, which is a scalar potential, and then a vector component, which is purely spatial, a purely spatial vector potential. And the 4 vector potential will be those 2 components, right? So there's the 3+1 split. And then how do we use this? So then for my magnetic field, I'm going to get it from the curl of the vector potential in the way that we always do, right? D J A K, right? Curl of a vector potential is my magnetic field, but now this is the spatial magnetic field. This automatically then, right, obeys the divergence-free condition, because if I take a divergence of a curl, I always get 0, right? Which is one nice thing about using the vector potential to evolve phi, which is actually how we do this numerically in a lot of cases. Okay, now I have a new set of evolution equations. Which are partial with respect to time of AI, that's a 1 form, is equal to minus EI minus gradient of phi. Cool. And then the other equation, partial with respect to time of the electric field, is going to be equal to di dj, second derivative spatially, j, vector potential sub j, minus d upstairs j, d downstairs j, ai minus 4 pi current density I. So that's Laplacian, right? There. And then this is the second spatial derivative of our vector potential, right? And this still satisfies this constraint, right? It must. And in order to see that, let me go ahead and erase this. Let's take that time derivative and see if this satisfies the constraints that I've imposed, okay? And so just taking dt CE, all right? Let's take the time derivative of that. And that's going to be equal to partial t di ei minus 4 pi partial with respect to time of the charge density. This is all equal to di of one big thing from my evolution equation, di dj aj minus dj dj Laplacian ai minus 4 pi the current density, like that. Close that, and then my notes start to cut off. Plus 4 pi di ji, the divergence of the charge current, right? And then that's equal to something cut off in my notes, so this should be fun. Di, right? Yeah, well, we just bring this in, right? Di, dj, aj minus di, dj, dj, ai, and minus 4 pi di of ji plus 4 pi di ji. And now if you start counting your various terms, because of commutation of these derivatives, those first two terms cancel. Same deal there. So all of those terms cancel to give you 0.
Second line, the first vector potential, or the next equation of. In the first, so you got like di, dj, the one up from there.
No.
The index on the first a should be right there.
Yeah. Is that right?
Yeah.
Then I have it wrong in my notes.
Otherwise, it doesn't. You can't contract like that right now.
Yes.
Do that, or the j on the d is up. I think should be on the
Hold on.
vector potential.
Hold on. That, I definitely, from the evolution equation, it's down. It's covariant in the evolution equation. Oh, it's this one.
No, that one should be right. That contracts properly. The other one doesn't. Which because you got a
true.
d, j downstairs, a j downstairs.
You know what I probably did?
I was gonna ask, which of those are I's and which are J's in the definition of E? No, del E equals various.
Okay. This one?
Yep.
EI, DI, DJ, AJ, DJ, DJ, I, big J, little I.
Okay. Thank you.
Should be first one should be di down, dj.
Where am I? Point.
Or di up. Sorry, there.
Here.
There should be an I on the first one.
DI up,
J down, and then
J down.
should be
J up?
J up, yeah.
Okay.
Because you invert, or you essentially apply the metric to each of them.
That's right.
From the,
Yeah, I think I got lazy when I was copying this over. Then let's fix this. Then all I have to do here to fix that is this. Yeah, I had the second line nearly right, so I must have just got lazy when I used the metric. Thanks. Okay. Suffice to say, in the end, all of these terms cancel and it's 0. And so our constraint is satisfied. Okay. So the use of a vector potential like this actually introduces gauge freedom. And it's in that choice of this scalar function, right? That's what gauge freedom is. I can add a scalar to my equations and not change the result, right? Because that scalar goes away when I apply the various differential operators. So that's where I get gauge freedom in these equations. And so solving the E and M equations in a 3+1 split involves specifying initial conditions for the vector potential and for the electric field and the charge and the current, right? And those 4 initial conditions, vector potential, electric field, charge, and current, have got to satisfy these equations for these constraints initially. But if they satisfy them initially, this analysis of the time derivative of these things based on the evolution equations would tell me that that's going to be preserved at all time. Which is another reason why solving E and M in a vector potential basis is nice, because the div B constraint is preserved automatically. So in E and M, this E and M is totally analogous to the 3+1 split that we will do for the Einstein equations, but our initial conditions and the variables that we're evolving are different. Instead of the E and M tensor, we care about the Einstein tensor, right? We care about essentially the metric tensor, right? How does it evolve in time? Not my electric field and magnetic field, but how does the metric evolve in time? Okay. Make some sense? So in a way, this is somewhat familiar to you from E and M. Okay. Foliations of space-time. This is my figure that I drew before, and I will draw again. X, and I'll just draw it in 2D space-time diagram. T0, T1, T2, T3. And so what I can do is I can define these hypersurfaces, purely spatial surfaces in my 4D space-time of constant coordinate time t. So everywhere on that space, it's still quite curved. It can be arbitrarily curved, but the curvature is described purely spatially, right? And so everywhere on that, the coordinate time t is the same. And I can define some normal to that surface, or to each of these surfaces, actually. This whole thing, we call that normal NA, just a normal vector to the surface. That's going to be important for setting up our evolution equations. Each one of these surfaces I will label as sigma, capital sigma, like that. So each separate foliation of space-time we will label as sigma. The entire manifold, the 4-dimensional manifold, we will call big M. So I take this big M, full 4D manifold, and I break it up into a bunch of purely space-like 3 surfaces called sigma that are separated by some time, right? Each of those 3 surfaces is at the same time. But there are many, 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 infinitely many different 3 surfaces at infinitely different times in this space-time. Right? It's been foliated, like pages in a book, right? We're treating GR like a flip book. There we go. It's not a terrible analogy. That's where the word foliation comes from. Right. Okay. Another key aspect of these things, okay, is that the surfaces sigma are non-intersecting. So each sigma does not intersect some other sigma, just like the pages of the book, right? That would be weird. Yeah. I mean, mathematically, it wouldn't make sense for the way that we break down the equations. It just fundamentally wouldn't make sense. And each one of these space-like free surfaces is some level function of a scalar we're going to call t, time, right? Okay, so now let's do some math with this. That unit normal is going to be important. And the way I've drawn it there, at least try to, and the way that we will use it mathematically is that that unit normal is going to be a purely time-like thing, right? Sticking totally out of this purely space-like thing, the free surface sigma. All right, so let's define the one form, omega A, which is going to be equal to the gradient of t, this scalar function that each one of these things are a unique function of, right? Level function of this scalar t. So that's the gradient t, all right? And we can close this by the following relationship. Antisymmetric part of the gradient of omega b is equal to the antisymmetric part of the Laplacian of t, and that is equal to 0. And recall, this is just an aside, but symmetric tensors, this is a notational note, pun intended. For a symmetric tensor symmetrization, this would be TAB plus TBA, and then antisymmetric TAB square bracket is 1/2. I don't have to put a square bracket there, but wouldn't hurt. TAB minus TBA, right? So that's what this notation means. Does that make sense? This is the first, I think this is the first time I'm writing this up on the board. So for instance, taking this, I could say that the antisymmetric part of the gradient here, this is actually equal then to 1/2 of the gradient A omega B minus gradient B omega A. If that thing is truly antisymmetric, that's 0, right? Same thing with symmetrization, right? The symmetrization of a symmetric tensor. Did I write that down? Yeah, I did. Right. Yeah, right. I'm not sure I said it right in words, but for a completely symmetric tensor, this is the tensor. For a completely antisymmetric tensor, this is the tensor, right? But that pulls out the antisymmetry or the symmetry of a given tensor. That's just a notational thing with these equations. Okay. And from this omega A, which is that gradient of the scalar function t, I can normalize it. And I can normalize with the metric. And so what I'm going to do is this norm of omega squared, the 2 norm, is equal to GAB delta AT delta BT. Right? And I'm going to define that to be minus alpha to the minus 2, where alpha is something we're going to call the lapse function. Because it's related to sort of how fast is time moving, right? How steep is that gradient in the time direction? The lapse. Okay. In particular, alpha measures lapses in specifically proper time. Between neighboring slices. So between these sigmas, right? All right. And we're going to assume, sort of by construction, that alpha is greater than 0. Okay? And that makes omega A time-like. And also, as a consequence, sigma is then purely space-like. And so that's the fundamental part of the 3+1 split, right? This assumption there. That splits these two things into a purely space-like and a purely time-like part. Okay. Oh, I don't want to erase my foliations. I'm going to be drawing them again. I know it. Let me see. We haven't even got to the unit vector. It's coming. All right. I'm going to erase over here. Questions? Okay. Question?
Question.
Yeah.
So can we just treat alpha as kind of as proper time?
Not quite, because it's not exactly the proper time. It's not exactly the proper time. It is related to proper time. But it's not a coordinate, really. It's sort of double gradient almost, right? Okay. All right. Now I'm going to define another one form, normalized one form, call it omega, and that's going to be omega A. I'm going to define to be alpha omega A. Now I'm using a little omega. But what this is the normalized one form, right? Because I've defined this as the magnitude. Stuck it in there, modulo a few minus signs, but what's a minus sign amongst friends? This thing is rotation-free, which is an important principle of it, one of the exercises in the book. And what does that mean? That means that antisymmetric A grad B omega C antisymmetric is equal to 0. That's the definition of rotation-free in this context. Right. The other thing that you can, well, I think that's all we need to know about that. All right. So now define the unit normal to my slices, sigmas. And now that's going to be this NA, which I've drawn on the board over there. And that is, all that is minus the inverse metric times the one form omega, right? I just raise the index on the one form omega, turn it into a vector, call it the unit normal vector now, not a one form, right? And so this points in the direction of increasing time, is the way to think about that, which is how I've drawn it over there. It is normalized and it is time-like, okay? And so what that means is that NA, which is equal to GAB, oops, inverse metric, GAB omega. Omega A, omega B is equal to -1. Right? So it has unit length. In this sense, if you recall, what is the magnitude of the 4 velocity
of a free-falling observer along that observer's world line. It's also -1. So in that sense, this is analogous to the 4 velocity of a observer in free fall, right? Just going with the flow of time at some point in space-time. And again, points in the direction of increasing time. Where is space-time flowing to? Okay? Okay, so now, with these definitions, I can construct a purely spatial metric. A metric that's going to live just on my slices. So, purely spatial metric. And we're going to call that gamma AB. It's going to be equal to the full metric GAB plus tensor product NA and B. That's how I'm going to define this thing. This is, in essence, a projection tensor. Which is how we want it to work, right? It projects out all geometric objects that are not in the space-like hypersurface. So anything sticking out of my surface, right? That wouldn't be just flat in this plane. This projection operator will get rid of them. Gone, they're 0, right? So if you were to apply this to, say, the unit vector, be 0. Because that's a purely time-like thing. So it projects out projection tensor that projects out all not purely spatial objects. So anything that doesn't live purely in sigma, that's going to get rid of. Okay. In other words, objects that lie along NA, the unit, right? Anything that is in the direction of NA, it's gone. Right? Anything that has a non-zero dot product in NA, it's gone.
If you have components in both, do you keep the space-like components, or it's gone?
You keep the space-like components,
Okay.
I think, would be the way to think about that, because it is projecting. Okay. This also, in analogy to the full metric, this we can use to compute distance, but now only in our hypersurface. So just like we would use the full metric to compute distances in 4D spacetime, we use the spatial metric to compute distances on sigmas. Okay. So now, if I were to take this and do this dot product, what I would get, NA-GAB plus NA-NA-NB, which by the definitions above, this is just equal to NB minus NB. 0. As it should be, right? By construction, this must be. By construction. Okay. Which is another way of proving that this gamma AB is purely spatial and lives only in sigma. No components out of that hypersurface, that spatial hypersurface. Space-like. Okay. We'll also need the inverse spatial metric. Which we get in a way that you probably could guess. use the metric components to raise indices of our spatial component, spatial metric, right? And if you work that out with our definition of the spatial metric there, that is pretty much what you would have guessed if I had forced you to guess. Okay. So now we'll need to use this metric to break up 4D tensors and 4D geometric objects into a time-like and a space-like component, the space-like component living entirely in sigma. So let's work with the temporal parts first. So projection operator to start this projection. It's going to be mixed components of the spatial metric, which is GAB plus NA and B, like that, which will turn out to just be a delta function AB plus NB, right? By definition of the metric, that's just a delta. Okay. And this will project four-dimensional tensors onto our spatial slice. That's how we can do that. Okay. We can remember that. We can remember that. Okay. So an example. Okay. So this is actually exercise 2.6 in the book. So let's say we've got some arbitrary vector VA. All right. Let's compute the following for this arbitrary vector VA. We're going to say NCGABAC times gamma A B V B. All right. Probably should have written this further over. Pardon me, I'm going to need more room. We're scooching over. NC gamma. Okay, so that's equal to, let's break this out, GAC all times delta AB VB. I'm just working this through from my definition of the projection operator there, plus N A N B VB closed. Let's see. A few more lines of algebra. NC metric GAC times delta AB VB plus GAC, and then I've got multiple components of my normal vector, NC, NA, running out of room, NB, VB. Can you read that? Sorry, ran out of room. But I just multiplied through. And this is equal then to NC, I just use this to raise and lower indices, and all that ends up being is NCVA plus NCNA NB VB. And, oops, that's B, right?
Should be NCBC.
Here? Yes. Sorry. And then that one's right? And then that is NC, get rid of that by the,
Do you have an upper A and a lower A for each end?
yeah. Which gets rid of them, right? You mean there? Did I screw that up? My notes are wrong. I think my notes are wrong.
Yeah.
Well, It's eventually equal to 0.
Right.
Clearly, I've got to fix my notes. How do I get this down? I screwed this up somewhere. I've got to use the metric to lower that. And
You can lower either of the NC or NA.
that's right. That's right. And so that then brings that down, right? And so then those go away. And then I get this. And since it doesn't matter what those indices are, well,
It should be, the first one should be like NC upstairs, V downstairs, and then the same thing on there with whatever index.
yeah,
Because it's a scaling.
that's right. All right, let me fix that. As I'm going through this, I went and looked at my notes. I'm like, that's not right. I have a mistake in my notes. I got to go online and fix that, and I will fix that.
First one goes to VA, and the metric will bring it down.
You want to fix it for me?
I
I screwed it up in my notes. I will fix it in my online notes. But suffice to say, this object is equal to 0, right? And so therefore, VA, VB is spatial, purely spatial. Sorry about the confusion. Thought I had it, and then I'm writing it on the board. I'm like, that doesn't make sense. Either that or I skipped a few steps in my notes, which I might have done. And then got confused. Okay. Which is exactly the property that we wanted for this projection operator, right? That's the point. Get back to the point without me screwing up indices again. Is that if I apply this projection operator from the spatial metric onto some arbitrary tensor or vector, I get something that is purely spatial. That's what I want. Right? That's what I'm trying to prove. Okay. All right. Okay. So projecting higher rank tensors is analogous. We do something like this. I'm going to define this projection operator. Looks like an upside down T, perpendicular operator, you might call it. Gamma AC, gamma BD, operating on some tensor CD, right? So just like we, yeah, question? Or you?
For that works out. The delta AB operator on BB, that makes the BA operate.
Yes.
And GAC makes the B index down. So then NC should be with the C should be up. And then the other one is the GAC lowers the C on the first end.
Yeah.
And then it becomes -1, and then it works. Or the BA should be a BC down in the first term.
Yeah.
Then
Oh yeah.
GAC
Yeah.
lowers the C.
Yeah.
Yeah, then yeah, it's -1 there.
Yeah. And then that's -1, and then all cancels. Thank you. Thank you. Okay. So that's projecting tensors. And then I can normalize this projection. And that's going to be capital N AB, which I'll define to be minus NA in lower B, which is equal to delta AB minus gamma AB. That's just a normalized projection. Okay, and then any vector in spatial and temporal parts will be, so I can express any vector to be delta A, B, V, B, right? Which is equal to gamma A, B plus the normalized projection A, B times VB, which is equal to the perpendicular projection VA minus NA NB VB. Temporal, spatial. Okay. I think we got time. Sure. Is that worth doing, or should we jump into the Riemann? Oh, we have time. It's worth it. Let's do an example, or at least apply this to an example that we will come back to oh so many times. The Schwarzschild metric. Okay. Use the Schwarz. Anybody besides Steve? Okay. In isotropic spherical coordinates, my line element, the metric, is going to be ds is equal to minus, we had this before, 1 minus m over 2r over 1 plus m over 2r, all squared dt squared plus 1 plus m over 2r to the fourth, all times dr squared plus r squared d theta squared plus r squared sine theta squared d phi squared. All right, these are called isotropic coordinates for the metric. Okay, so then for the spatial slices, every once in a while my sigma gets a little squirrely, with some constant scalar time t. Okay. The one form component, remember omega, is just going to be equal to 1, 0, 0, 0 in these isotropic coordinates. It's normalized in that way. Okay, and so then remember my L2 of this thing is G AB grad AT grad BT, which is defined to be the minus of the lapse to the minus 2. So looking at the components here, looking at this is pretty easy. Look at the components of my metric, which is this thing right here. And from this, I can get the lapse, which is equal to 1 minus m over 2r over 1 plus m over 2r. Just this part, right, of the metric. Okay. All right. Now, let's get my normal vector. N, A in one form, is going to be minus G alpha beta omega GAD. I switched to Greek. It's the first time it's happened today, though. Which is 1 plus m over 2r all over 1 minus m over 2r times, I'll just write it in this compact notation, right? A diagonal matrix, like, well, it's not a vector, 1, 0, 0, 0, right? It has only time components. Right? Has only time components in these isotropic coordinates. And then the spatial metric projecting sigma gamma AB is going to be equal to 1 plus m over 2r to the fourth times the diagonal matrix, which is nothing but, oops, just looking at this part here, 0, purely spatial, as it ought to be, 1, because that's just multiplying there, and then r squared, sine squared, theta, on the diagonal, all their components 0. So it's still 4D, right? Like we're still using AB here. So it goes from 0 to 3. The time component, 0. There is no time component, right? Okay. So that's just how you would take the Schwarzschild metric and break it up into a 3+1 decomposition. And then all the other things that we talked about, we could do black holes in a 3+1 framework, applying these spatial metrics and normal vectors. Okay. All right. So that's that. Let's talk about derivatives in 3+1. Okay. So what we're going to do is project the 4D gradient onto sigma to get an operator that is our gradient in sigma. Okay? So for some scalar field, I'm going to define this as capital dA. So this is going to be my covariant derivative in my slice sigma, which is going to be equal to projection of the full gradient like that, right? So I'm projecting the full gradient using my projection operator into my space, my spatial time slice sigma, spatial slice sigma. And I'm going to define that to be this capital D. So that's now a spatial covariant derivative operating in sigma. Okay, for some scalar field F. All right, similar for tensors, covariant derivative of that. I'm going to define, similarly, I'm just going to use extra spatial metrics to do the work for me. Operating on a mixed component tensor like that, right? So I skipped vectors. All right. With this definition, you can work this out for yourself and apply it then to the spatial metric. But if I were to do that, I would end up with dA gamma B C is equal to 0, which is what I want, right? Remember the gradient, the full gradient of the 4 metric is 0 in 4D space-time. So we'd like to preserve that property for the spatial metric in our slices sigma. And so this definition does that. All right. And then the 3D connection coefficients in the 3+1 split are going to be A, B, C is equal to 1/2 gamma A, D, all times partial derivative with respect to C of gamma D, B, plus partial derivative with respect to B of gamma D, C, minus partial derivative with respect to D of gamma B, C. Which is exactly how we wrote down the connection coefficients, just replaced in 4D, in full space-time, just replacing spatial metric with the full metric, right? But the ordering of the derivatives is the same, the signs are the same, and everything. All right. The 3D Riemann tensor is then R, A, B, C, D. I don't know if the book says this explicitly, but if you're reading through, Whenever they mean the 3D Riemann tensor, or generally 3D objects, this fourth index is last. But when they mean the 4D Riemann tensor, they put the up index first. Doesn't make any difference, right? I think they just use that as a signal of which version they're talking about. Partial with respect to B of the connection coefficient, that got cut off. Super. I'm going to have to guess, which means I'm going to get it wrong on one of these, so watch me. DAC minus partial with respect to A of gamma DBC plus gamma EAC gamma DEB minus gamma EBC gamma DEA. Again, completely analogous to the way that we construct the Riemann tensor in 4D. But now we are using these 3D connection coefficients, which depend only on the spatial metric, which has only spatial components. Okay, and this Riemann tensor obeys the following properties. 2 times the covariant derivative antisymmetric part of it of some thing, WC, some vector WC, is equal to Riemann tensor CBA WD. And then this Riemann tensor D upstairs CBA times the normal vector ND 0, right? Dotted with the normal vector, contracted on that index. That is 0. All right. And this Riemann tensor is purely spatial. It doesn't have any time components. And so in that sense, since it doesn't have any temporal components, it is lacking information that the full Riemann tensor contains. The full Riemann tensor contains information about the curvature of space-time, not just space on some temporal slice. And so we might say that this 3D Riemann tensor contains information only about the curvature intrinsic to the spatial slice I'm working with. And that's what we're going to call it. We're going to call it an intrinsic curvature to that temporal slice, that sigma. In order to, and I'm not going to, I didn't think I was worried I wouldn't get to extrinsic curvature. There's too much here for me to cover, so I will just bump that to next time and just finish talking. So in order to evolve this forward in time, okay, so everything that we've developed here so far has been on this 3 slice, right, of sigma. In order to understand how the metric is going to change in time, I need information about how space-time is curved out of my 3 slice, right, in the direction of increasing time. Because what I want to do, I've split this up into 3 plus 1. I want to make the analogy with an initial value problem, so I want to integrate forward in time. In order to do that, I need information about how these metric quantities are changing in time, which is determined by objects that lie outside of my time slice. So I can't get that purely from things that have been projected down into just my sigma, my hypersurface. So if this is the intrinsic curvature, I'm going to need what's called the extrinsic curvature, which tells us about the curvature of space-time out of the hyperslice, which tells us how things are going to evolve in time. In analogy, it's like the velocity, right? So everything that we've done here sort of tells the steady state story, right? Where is everything at? And then what we need is the extrinsic curvature, which is like a velocity, which tells us where's everything going. And that's how we will treat it, very analogous to location and velocity. And that will be the extrinsic curvature. And we will develop that next time because it involves introducing all kinds of things like things called Lie derivatives, which are fun. Okay. Questions? All right, read chapter 3 for Tuesday, which, you know, if you haven't already, it'll review some of this stuff and probably make a lot more sense than the past 80 minutes have, maybe. And then I don't know that we'll get through the rest of chapter 3 on Tuesday. It might take 3 lectures to get through chapter 3, but it's kind of an important chapter, which kind of sets the stage for everything else. So I think I might just take 3 lectures next week. I was very rigid about the pacing for the stuff we did from Thorne and Blandford because I knew we could get through it a chapter a week. But here, it's the Wild West. I don't know how long it's going to take me to get through some of this stuff. So we'll take as long as we need. All right. Get working on those TOV solvers. And feel free to ask questions on the Slack or anything. Like, this is not supposed to be a mystery. I just want you to do it. So if you're hung up on something, ask. The point is to get the experience. All right. Thanks.
So great.
Yes.
Do you have an index on?
There's something right there.
No, it is. Or the night, I've texted you. I don't know if it's assignment.
So at one point.
So the B should be the thing that divides.
So, yeah.
Step 1.
I think I'm going to check that.
I wrote the wrong thing. I skipped something. Thank you. Thank you. Alfred noticed something I forgot to write that is in my notes. I was going too fast. There's a missing gradient operator here, right? But it's correct in my post-it notes, so go fix that. I just left out a gradient operator here to get rid of and contract on this D index. And there was no differential operator on the right-hand side. That didn't make sense. Yeah, thank you. Oh, let's kill this.